Okay, so I have uh, so let's recall what we did last time. So we did we're trying to prove the Sohn's lemma. So this is Sohn's lemma. So if you have a partial loaded set uh, such that every chain has an upper bound, then the whole partial loader has a maximal element. We're not guaranteeing that. We're not saying that there would be like one maximal. It would be uh, exactly one maximal element, but we'll find one. Okay. Uh, and a chain is a totally ordered subset. And and in here the chains can be empty sets. Okay. So for example, if a chain is empty set, then any element in the set would be a upper bound for that set. Okay. It, now so this is the notation PXC, and sometimes I'll write like PCX. So if you have a chain and an element in the chain, uh, so this PXC is the initial segment, so everything that smaller strictly. Um, so this in here is strictly smaller than, okay. Remember when I wrote the Sohn's lemma, I'm using this notation, okay. Now, and so for a contradiction, we assume that this doesn't have a maximal element. Okay, so that means for any element, uh, 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 okay, so we assume that the partial, so this partial order doesn't have a maximal element, and that allows you to create this kind of this map. If you take any chain, so these are the chains, set of chains, and if you take any element in the chain, and now every chain has upper bound, so we have A as upper bound for the chain, and then but since A is not the maximal element, we can find something even bigger. Okay, so what we have really done is uh, we have shown that for any chain we can find the element that's in the partial order, but it's not in the chain. That's strictly bigger than every element in the chain. Okay, so let me not happy with the not happy with what happened in here. Let me rewrite this set again. may okay, so the what we have here, let me rewrite this set. So what we have here, for each element C from your set of chains, so we have call it B in L, such that for all x in your chain, x is strictly smaller than b. Okay. So what we have here, we have a collection of sets. For each element C, there is a collection. There is AC, and like what we have shown so far, we know that this AC is non-empty. Okay. Now, for all chain C in here, AC is non-empty. Okay. Now, you can so like now once you have this, we can it looks like we can define this map, this function f from collection of chains, set of chains into here. Okay. Okay, for so let me draw this here. So there is a what you're trying to do is this f is a map, and then also like we have this condition f of c is so you want for all c in here, f of c belongs to AC. Okay, so that's what we're after. Okay, for each chain, we come up with the element that's strictly bigger than all the elements in the chain. Okay, and so the existence of f is given by axiom of choice. Okay, so this is where we use axiom of choice. Good. Can you guys put the video, send it? I know that Isita has some issues with the video. Good. This is clear, right? Okay. Now, so now we have written it a little bit in a kind of a nicer way that that it's clear that what we're doing here in the construction of F is we are really using the axiom of choice. Okay. So the axiom of choice is when it appears, it's actually trivial. every time. You can like easily miss it. Okay, good. Uh, Now, what we are after is a set of this form. So we need to you start with the uh, empty chain, and then you apply this F delta map. F delta is if you have a chain, and then you kind of attach the this next element for the chain, and then you create a construct a larger chain. Okay, so and in this way you start with the empty chain, and then you go get to the next one, next chain, and next chain, and then you create a, this kind of sequence of chains that are that the one contains in the other one and the other growing. Okay, and when you take the union of those things, you will get the uh, you'll get the chain you want. Okay, okay, so that's the idea of the proof, and so this is written here, and if you but when you consider the union, you'll get in trouble. Okay, now so we are after this set O, but you cannot do it like this way, doing dot dot dot. Okay, so the main argument of the proof is to just find a way to construct this thing. Okay, so the way we construct it is we define collections of subsets that satisfy that behaves like this one. Okay, where you get the so inside. Okay, inside, if you take any element, the next element is actually constructed using this F delta OF. Okay, so we look for those things. Okay, and that's the motivation for this definition. Okay, so not confirming. Uh, I mean, this is not a standard terminology. But, so existence of a set like this is actually confirming O. It's like not the whole O, but part of O. Okay, so that's the idea for defining this. Okay, and the definition is A is a subset of X, and A itself is well loaded. Okay, so not just total loaded. So remember the chains are total loaded, but this one we want well loaded. Okay, and this is telling you how this set A is actually really constructed using F. Meaning that if you take any point and you look everything below it, and then you get a chain, and then you apply F to that for that chain, and you land in back in X. Okay, good. Nitika, any questions?
No, I think so.
Huh? It's fine, right? There might be like tiny issue, but in the way that I have written O, but the O that I wrote is it's kind of very um, it's very informing. Okay. Uh, Now So there's no issue with this definition. Now, so what we want to show that these sets, conforming sets, are actually they're kind of nested in the sense that one set lies completely inside the other one. If you take like two conforming sets, either they are equal or one sits completely inside the other one as an initial segment. Okay, good. And so let me start the lecture today by so the February 2nd. So this is lecture 1, part 2. So the kind of the lectures are organized by the topics. So might take like some lectures might take a lot of sessions to complete. Okay, good. Okay, so let's recall claim. Claim is this. Proof of the claim. So what you want to show that if you have two conforming sets, then A and then they're equal or one is inside the other one. Okay, so it's enough to assume that A has elements that are not in B, and then we show that the B has to be completely inside A as a segment. Okay. Okay, so let me go here. Let assume will show that B is equal to P x of A for some x in A. Good. Now, the picture to keep in mind is this one. Okay, so the pictures helps, but when you actually write things, you're not you get the ideas from the picture, but you're not referring to the picture for the proof. Okay, the standard thing. Now, so and I gave like a fake proof to kind of tell that how we're gonna prove this thing, meaning if you have this and if this is your x, and we pick x to be the smallest element in b minus a minus b. Okay, and then we want to claim that that x we want is this actually. Okay, and And if this is not the case, you'll have some additional elements in B, and so on. Okay, and then we get to kind of the smallest element in here, and then you go one level below. And because since A and B are both confirming, if we get our hands on the something in here, and both A and B were constructed using F, and then you'll get a contradiction by saying that if you apply F to this element, and in one side you will say that you get to B this element Y and get here. So the point is, like, we use the same function for all these conforming sets, and you will find the kind of we say that the branching is not allowed. Okay, because both A and B are confirming, and you see they have the same property with same map. Yeah. This one. Okay, so the next element is constructed by applying F to this thing. Good. I know I'm going back and forth between elements and initial segments, and the element part I write this W to, I mean, this is to give the idea, and you'll notice that what we have to deal with is in general, we cannot go back in well-loaded sets. We can move to the next element, but we cannot go to the previous element. So, but this W is going to get replaced by initial segment. Okay, good. But this is the idea. You cannot branch off. Good. Okay. Now let me write so we pick this X, our candidate. Let X. We'll show that this happens. So take X to be the minimum of A minus B. Okay, and good. Now if this is the case, so let's see. And we need to show this. Okay, and actually one direction is easier. Okay, so so everything in here, why this is the case? So this is true. If this is not the case, then you have a if not, there exists simple B in B, and it is not in here. Okay. Now, what does this tell you? Okay, so so if this is not the case, so we have sorry about it. Okay, so there exists simple A in here. I wrote the negation for the other one. Okay, so that is not the case. There is the element in here that's not in B. Okay, good. But now this A is actually strictly less than X, and A is in A minus B. Good? Agree? Zenith? Okay? But this is a contradiction, because uh, this is a contradiction because we know that the X is the minimum. Okay? These things are like kind of when I draw if you draw those two lines, this type of picture. That's my set A, and this is my set B. And we have X in here. Okay, so X is the and even when you draw this type of pictures, you automatically assume this type of things. Okay, good. Now, so this side is easy. It's the half of the inequality. Now let's do. We'll show that B is inside here. Okay. Now, if not, any bye Tata is teaching. If this is not the case, then we have B minus pxa non-empty. Good. And like we get this is my set there. So that means the B has more elements that are not in the initial segment at X of A. Okay. And then we let Y be the, minimum of this set. Okay. So this is my y somewhere here. Okay. So now we are kind of trying to get at this. Good. So you consider the so you consider this guy. Let me call this thing W. Whatever the thing that we are after, okay? Uh, so so uh, so the we have stuff that see the like in here we draw this thing. There are elements in A, okay, and then there's elements in B, right? It's I mean this set W is initial segment of two different sets, and we don't know whether they're equal or not. I mean, you draw it, and you say that it looks like they're equal. Okay, so you consider this set. Consider uh, this set initial segment at y of B. Okay, and then and then and then we look at, see, like we had x in here, and we are trying to look at this segment here. I mean, the picture is very misleading, but we have to there's two different types of initial segments. It's happening here. I mean, those should be equal at the end of the day, but we don't know that yet. Okay, so so this is kind of the candidate for W in one side. Okay. And we have note that if you apply F, we'll get Y when you apply F to this set. Okay, but to kind of move forward, we want to show that this exact set is the initial segment of A. Okay, it is not obvious yet. Okay. So we are looking for we need to show that this set is the initial segment of A. So it'll be nice if this W is equal to the initial segment of A at X. But the kind of the way to go is to consider this guy. Consider C. That is the minimum in A 11:43. Come back at 11:43. That is teaching. Today is Sunday. Sunday Tata teaches. So we have a minimum of in A P Y B. Okay. And this set, we don't have to worry about the existence of this because this is actually this is a bigger subset than A minus B. Okay, and we know that this is non-empty. Good. Now our claim. We want to show that if we take the segment of A at C, and this is going to be same as a segment at Y of B. Okay. And if we get this, then we can apply, then we will get, then you'll get C equals F applied to the segment of C of A. Okay. So that we can, so this is kind of this set becomes, this W becomes the branching. Okay. Good. And and then if this happens, we have so this is same as PYB, and we will get that this is equal to Y. And it looks like these C and Y actually coming from two different directions. Okay, and you'll get a contradiction. Okay, but before we get there, let's prove this thing. Okay. Any questions? Questions, Nitika?
No, sir.
Okay, now, so let's so let's prove this thing. So we'll prove this one. We'll first show that PC of A is a subset of P y of B. And so if you take element alpha in here, and what do you have here? So we have alpha is in A, and also alpha is less than C. And this should give you this working.
I'm just building a place to sit.
You can't do that. That is teaching. That get distracted. Go. Don't mess with that. Then can you get from here? And actually, this should be easy. This follows from look in here. So if you take a alpha that's in A, and which is strictly less than C, is it? And if this alpha is not in PYP, that means that alpha would be a candidate in here. Okay. Will be in A, and it'll be, if it is not in PYP, then it's element in here. But we know that Z is the smallest one, right? So then it'll get contradiction with this. Okay. So this side is easy. This side is we prove this side. Let me call this thing. Okay, so on the other hand, let beta We'll prove the other side. So if we take so we have shown one direction now. We need to show this one. Okay, let's go. Let's start. So let me. I mean, we have been carrying this thing out for a while, but let me write down what we have done so far. So let me. So we assumed we started with assuming assume A not equal B non empty, and then we pick X. Not pick. We take X to be the minimum of B minus A minus B. And immediately when we do this thing, if you look at all the elements that are smaller than X that are inside A, that's the initial segment at A of initial segment of A at the point X. So all these points, elements in here, they cannot be in B because so all these things has to be in B, because if they're not in B and that element is going to be element of A minus B, and that means we have found an element that is smaller than X, strictly smaller than X, and that's inside the set A minus B. So we have this. Okay. So every time we carry out this process, and we ended up with something like this. Okay. And we have been doing this thing for a while. So P X at A is a subset of B. Right. And in here, this X is actually, and we then we assume that this is not a that it is not equal. I mean, this is the thing that we want to prove, that we want to show that Px equals to B, but if that is not the case, then we take Y to be the then we pick Y to be the so this is and then we have 2. We pick Y to be the minimum of minimum element in B that's not in Pxa. Okay. And again, like as soon as we do this thing by the same process, same argument as in 1, we get that everything that's strictly less than Y that are in B has to be inside Pxa. Okay. And then the third step, we assume that I mean, we want to show that these two are equal, but again, if that is it is not the case, we assume that this set is non-empty, meaning that Pxa minus Pyp, and then we take C to be the smallest element in that set. Okay, and again, like immediately when you do this, you get this inclusion. every time when you pick a minimum like this, you automatically get this inclusion. And we have sometimes, I mean, we proved this thing already. But now, so what we need to show that this star, statement star, is about showing that basically this other inequality, okay? And if we assume that assume that we have a t that's we assume that this is non-empty. Assume that, then I mean, we can keep going and define whatever, like t to be the minimum of this set, but we don't have to do it. So let t be an element in here. Yeah. Okay. So it looks like, you know, we're doing this thing and we're not getting anywhere. So if you I mean, we do gain something. So what we gain is this. Like uh, if you look at the this idea, or like doing something like this. I mean, this is wrong, but what ended up happening if you start to do things and we pick the minimum like that, I mean, when we draw this line, we automatically assume that whatever the kind of the initial segment is kind of shared by both A and B. But in reality, what happens? So, uh, for example, so in here, what we are saying that initial segment of A might not be in B, okay, completely. So it is in B, but there might be uh, it is in B, but like in here, for example, this one had initial segment at X of A and initial segment of uh, B at Y, and then when you draw these things, those looks like the kind of same line in here, but the problem is they might not match. There might be more elements. So even the tails, I'm using the word tail as the uh, initial segment. Um, anyway, but once you go inside and inside and inside this way, so we have gained something. What we have gained is now this element t. So this element t now, because it's in PYB, uh, it is in PYB, but PYB is a subset of PXA. In particular, it's a subset of A, right? So this element is in A. And also this guy, T is in PYB. So that's also in A, also in B. Okay, so now that we have so you get here, these things are in both sets. Okay, and then Yeah. Now, so where is this T in A? So so let's look at this here. Okay, if you look in here, what can you say? So this T is in A, but it's not less than or equal to C. Sorry, it cannot be strictly less than C. So that means this T has to be greater than or equal to T. Okay. And again, this T is in here. So that means it's in here. That means it's strictly less than X. Okay. So that's where this T is. And if you look at the other element, can kind of locate where this thing is inside B. And yeah, we can only compare it to Y. So you can say that T is in PBY. So that means T is in, that means T is less than Y. Okay. Now you'll get in we'll get in trouble. So what we have, so we have a C from this and this, from these two inequalities. From this one and this one, we get C is strictly less than Y. Okay, and also we have from these two, we have C is strictly less than X. Okay. Now we have so if we get in trouble now, because if C is in B, if this is the case, what happens? If this is the case, we get now see, if C is in B, then C is going to be because C is strictly less than Y, we get C is it's going to be actually going to be in P YB. Okay, but we picked when we picked this C, right here when we picked it, this C was the minimum. Yeah, when we picked this C was the minimum of here in PXA, but that's not in PBY. Okay, so that contradicts the 3 assumption 3. Okay, and if C is in B, C is not in B, if C is not in B, but C is in A, so that means C is in A minus B. But if C is in A minus B, and then we know that we pick X to be the smallest element in A minus B, but we have this. Okay, so that's also a contradiction. Okay, so this shows that. So we finally got something. Okay, so we have this setup. So we have proved the equality here. This is equal. Okay, so we have P CA is equal P YB is equal P XA. Oh, it's a inside P. So that's where we are at. Okay, now this is our like now we kind of found the initial segment that that's equal. So this was the thing that we are after. Okay, right, and so for example, talked about this set W here. Okay, so we are looking for a kind of branching point. I want to say that because both these sets are not constructed. I mean, they satisfy this property like we call it like inductive step where the next element can be obtained by applying the function f to the that set. Okay, so we kind of figure out a fork or like a branching point here, right? So that was the idea of the proof for this whole time. Okay, so we finally got to a place where we can apply. And let me call it by induction step. This is like you're not using induction, but I'm calling this thing the induction step. So we have C equals F of PCA and F of PYB. So now we get this C is equal to Y. Okay. Now this is like you think of this as a kind of a sip, and then you have like if you have a thing that forking going like this, and then you say like no, these two has to be equal, and then you kind of move up like moving like a sipper, right? And so you can go up now. So now so let's see now. Note that now this element is in A because Z is in A and also Y is in B. So this is now in A intersection B. So, and if you look inside A, you get what do you have? We get so now you can. So the thing to notice is so I mean in the proof we assumed this one, okay? But this assumption is now gone. Okay, so we got a contradiction inside that step, but we're still working in the kind of outer layer of the proof. Okay, so we haven't reached the full contradiction here, like inside the proof you made assumptions, and you're kind of going up. Okay, so now what do we have? Now we found out that y is in A, but where can we locate it? So if y is in A, so now we so we have y, which is equal to x, and which is equal to c. And where is our x? X, so y, so y is in here. Y is this element, y is in B, but it's not in Pxa. Right? But we know that now y is in A, y is in A, but not in Pxa, meaning it's an element that's greater than or equal to x. Okay. Because y is not in x. Okay. Now and in here this y, no, y cannot be equal to x because y was chosen to be not because we already know that y is in B, but x is not in B. Okay, x is not in B, so y is in B, so x cannot be equal to y. Okay, so we have this setup. So we get x is strictly less than 1. Okay. Now what happens? If you look in here, so PCA, this set here, equals P YP, right? It's a thing that we proved, but the C is equal to Y, so this is same as P YA. Okay, so now that is the case. Now from this we get, see, PYA, this is all the elements in A that's strictly less than Y. So that means this X is going to be in here. Okay, so we'll get X in here. X is going to be element in here. Okay. So now X is an element in here. So if X is an element in PYA, but now this is equal to PYB. But this should tell you that X is in B. Again, there's now this contradiction. Okay. So this contradiction is for the assumption, this one. So we got like two contradictions there. It's like a first assumption, and then inside that assumption we made another assumption, and then you got a contradiction in there. Then you prove something, and then you got the second contradiction that tells you that this we cannot choose this y. So this when we when we choose this y, the assumption was that this is strictly strict subset. Okay, so what we have is so that means we have proved that this is actually an equality. Okay, so Pxa is equal to B. Okay, so that means we showed that the set B is actually an initial segment of A. Okay, and when you go in here, and this is the assumption. We have this assumption. We got there, and then if you by symmetry, if we assume that B minus A is non-empty, we will be able to find some element in B such that A is equal to an initial segment at that element of B. Okay, so by symmetry, symmetry you have the other side, and so the other possibility is A is equal to B. Okay, so these two sets are these confirming sets. They're either equal or one is the initial segment of the other. Okay, and this is a good time to work on this problem here. Comparability, not compatibility. Okay, and this is saying that given any two well-loaded sets, you can do this. Okay, and you will use Son's lemma to prove it. Okay, so we're still inside this proof. Now, let's move on. So we have proved this claim. Okay. Right. So we have these confirming sets, confirming subsets of X. These are well-loaded sets that satisfies this induction condition, meaning the next element is created by applying F. Okay. Now, so the next step is if you have these confirming sets, now they're one inside the other, so that means you can take the union. Okay, so that's this step. Okay. I mean, this was just the fake proof and the idea, but now we're doing this step. Okay. So we consider So let me finish this thing. Similarly, if B minus A non-empty, then A is B YB or so on. So, or the other option is A equals B. So this finishes proof of the. Now, consider the set A O, which is the union sets A is confirming. Okay. Claim this set O is confirming. I'll call it M. Okay, so you need to show that first thing is M is well loaded. And for all X in M, X equals F P X at M. So let's prove first thing, let's prove that we need to show that M is a totally ordered set, because it's just a union of sets, right? So because it's a union of sets, you don't need to prove that it's a partial order, because this M is a subset of our partial order X. So you don't have to prove that it's a partial order, but you still have to prove that M is a well order. M is a total order. It's totally. Okay, and then we will show that M is well loaded. Okay, and then we prove this. See, satisfies the induction property. Okay, so now proof of A. So to prove this thing, So you show that things inside M are comparable. So let X and Y be two elements of M. So X then X is an element of A and Y is an element of B for some A and B confirming sets. Okay, now what happens? These A and B are comparable. Uh, one sits inside the other. So without we can assume that A is sits inside B. Okay. In other words, A is equal to some initial segment of B. So if that is the case, then you will get both X and Y are in B. Okay, if both X and Y are in B and now B is a well-loaded set, so X is less than or equal to Y, or Y is less than or equal to X. Okay. So this point B, we want to show that M is well loaded. To show that M is well loaded, we have to pick a non-empty subset, and you have to show that that has a minimum. So let W be a non-empty subset. And we need to find the minimum of W. And now the thing is we cannot assume that W is inside the one of these confirming sets which are well loaded. But actually, if you're looking for a minimum, so you kind of need to. It's enough to find a minimum of the kind of the initial segment or like some tail part of a set. So let alpha be an element of W. Will show let me do the full proof of this thing instead of putting things in homework problems. Okay, so it's very tempting to like keep these things out homework problems. Okay, so let alpha be element in here. Now consider and then there exists a actually this alpha is in A for some some confirm. Set A. Okay. See the okay. Let me, even though I'm not putting things in homework, let me write down what I'm trying to do. So what I'm trying to do, it is enough to find the minimum of the set of beta in W that are less than or equal to alpha. Okay, and we'll show that the minimum of this is the same as the minimum of whole W. Because all the other elements in W are going to be strictly greater than alpha. Okay, good. Now, so let alpha belong to A for some A in, let me call this set C. Call this set C. Okay, so that's a set of confirming sets, confirming subsets. Let me call this instead of C. I think I used we call this thing O. For some A no. Okay, the set of confirming sets, confirming subsets, call it O. You know, there might be some notational inconsistencies with the fake proof, but the proof should be clean. Okay, notation it. So now, now what do we have here? So call this thing W alpha. Okay. Now it looks like we can find the minimum of W alpha by using the fact that A is a well-ordered set. Okay, so but we have to show that that W alpha is actually a subset of A. Claim this W alpha is going to be a subset of A. And the problem is we don't know. It looks like this W alpha is a confirming set. It is going to be, but we don't know that yet. Okay, so we might probably have to use the that confirming sets are comparable. That one. Okay, so so let's go this way. So let beta be an element in W alpha, and let's assume that beta is strictly less than alpha. Because if beta is equal to alpha, then there's nothing to prove. Okay, because alpha is already in A. Now, so now beta is in. So this beta is in W. So that means beta is in. So beta is in some confirming set. There exists some B in our confirming set such that beta is in B. Okay. Now
Found you.
yes, you found me.
Write this up. Can you write this up?
Give me a second. Yeah, so we need to show that. Let's see. So when we need to just need to get this element beta uh, in A. So I mean, I have these two confirming sets A and B. So one is inside the other one. So if B is inside A, that'll get beta inside A. That's what we want. But if A is inside B, that will get alpha inside B, and yeah, that side works too. I was thinking of just constructing a kind of new confirming sets This is basically the initial segment of beta at the point inside the set B, and then you add beta to the end. So that would be a well-loaded set, and that would definitely be inside A. But yeah, other direction is okay too, I think. So so we have two cases. If B is subset of A, or B is equal to A, then it's immediate that beta is in A. Okay, so that part is fine. If A is equal to some initial segment of B at gamma, if this happens, so we have alpha is in A, so that will tell you alpha is in B, and alpha is strictly less than gamma, and we know that now we know that beta is less than alpha, so this will tell you that beta is less than gamma. Okay, and we know that beta is in B, so beta is going to be in P gamma B. So it is equal to A. So in that case, we get beta is in A too. Okay, so that means we have showed that so this W alpha is a subset of A. Okay. So we have proved this claim. So if that is the case, let M to be the minimum of W alpha. Okay, and this exists by the fact that A is a well-loaded set, and W alpha is non-empty because alpha is W alpha. Okay, and now what we have, so the final claim is M is actually equal to the minimum of W. Okay, so I will leave this thing as exercise because we have so I'll leave this thing as exercise. So exercise I have think I have written 12 so far. So we call this thing 13. Okay. So that means we have shown that so we have shown that M is well loaded. Is now finally we need to show that proof of part C. We need to show that this set W satisfies this W satisfies the induction condition. is this. Okay, so let alpha be a element in M. So we need to show that alpha equals F applied to P alpha M. Okay, now it looks like we played with P alpha M already. I mean, we didn't so this is not equal to P alpha M. Okay, we didn't prove that these are like, oh, no, I mean, definitely not. I mean, this is not a this this W is not a this W is not a initial segment or anything. So we didn't play with this thing yet. Okay, so let's so you need to show this thing. So I mean, the strategy is this type of uh, induction conditions hold for confirming set. So we show that this is actually a initial segment at alpha for some A. Okay, so let uh, alpha belong to A for some A is confirming. So claim P alpha M is same as P alpha A. How do you prove this thing? So let's do it. So first we note that that A is a subset of M, because M was created by taking all these unions. So that means P alpha A is a subset of M, and but everything in here are elements of M that are strictly less than alpha. So that means this is actually P alpha A is actually elements of. Okay, so we have this, and the other side. Um, yeah, so if you take, let beta be an element in P alpha M. Then and beta will belong to A. And we prove this thing, then since beta is already less than alpha, so this beta would be element in P alpha. Okay. So this star, this step this step we proved in we went through this thing earlier here. Okay. So in here, like when you assume here, you pick an element in beta in W alpha that's strictly less than alpha. We are not using any information about W alpha. It's just a set, right? So this same proof would go. Okay, let me keep it as exercise. So exercise 14. Pro this condition, but it is like it's already done, but it should be easy. Now where are we at? So we have this shown, and now then so this is double star. So since A is a conforming set, we have that induction condition for A. So we have alpha equals f of P of alpha A. But we showed that P of alpha A is same as P of alpha M. So there is a tiny issue. I mean, it looks like an issue, but it's not an issue. So we are not, see, like more like this completes the proof that M is a conforming set too. right? And but we have used this notation before that. But with this, remember this F is defined for any chain. Okay, and we have it doesn't have to be confirming to be able to use this F. We defined F for like a larger collection of subsets of capital X. Okay, so now this completes the proof that uh, this completes. This completes the proof of the fact that M itself is confirming. Okay. This. Okay. Now, now we are reaching. I mean, in Swan's lemma, we're proving Swan's lemma, and you're trying to get to the maximal element, and um, we are getting towards contradiction. Okay, and I don't know if I said that M is going to be the maximal element that we are after, but that's not true. Because what we're trying to get at is a contradiction. We assume that there is no such maximum. Okay, so now, so all we have is now let me go back to the proof outline. So we have shown something like this. Okay. Okay, so we have shown something similar to this. So we have our M, which is this union of confirming sets. And the next step is we need to apply F delta to M. Okay, so the recall F is the one that gives the element that's strictly bigger than the chain that you started with. And then F delta is just the chain that's obtained by attaching that strict upper bound. Okay. So F gives you a strict upper bound, and then F delta is this one. Okay. Now let's go back. Next, we consider F delta applied to M. This is basically M union with F of M. Okay. Let me call it V star. So now not that m, f delta m, that is call it m delta. M delta is the m delta is not equal to m, and it's actually m is a strict subset of m delta. Okay, m delta has this B star element. Okay, and but we will show that claim that this m delta is actually a conforming subset. Okay, now we call it exercise 15. But let me just see. Remember, we had to prove three things. Okay. So the first one, we need to show that so if you want to show that M is conforming, you know, show that it is total loaded and then well loaded and satisfies the induction condition. Okay. So totally loaded is fine because we have capital M. We have capital M, that's a total loader. And then you're attaching an element, just a singleton element that's bigger than everything. Okay. And so you can show that this union is a well-loaded set. And I think this is very similar to problem 10. So for the problem 10, we actually tell you how to construct a new how to like add two partials, add two total loaded sets. Okay, so in this one you can think of it that way. But this is going to be a well loader. That's okay. Because if you take any subset of M delta, if it has any element in M, then it's enough to find the minimum of that subset subset intersection with M, and then you get a minimum, and that's going to be the minimum that you're after. And the other case is that subset contains only B star. In that case, the minimum is B star. Okay, and the third part is this induction condition. Induction condition comes from, we need to show that for every alpha in M star, as M delta, you want to show that alpha equals f of p alpha f of p alpha M delta. Okay. So there is like two cases. If alpha is equal to B star case, and the other one is alpha strictly less than B star. if alpha is strictly less than B star, and we are actually dealing with initial segments of M instead of M delta. So since M is confirming subset, we have that induction condition. And if alpha is B star, then the initial segment at B star is actually M. And you want to show that if you apply F to that, you'll get B star. But that is how we define this element. Okay. So that's in as a this condition. Okay. So I'll leave it as exercise, and that's fine. So now where are we at? Okay, so now we're done. So now if you look at M, so we have M to be the union of all the sets in A, such that A is in this O, but we have shown that M star is in O. Sorry, M delta is in O. If M delta is in O, that means this will give you M is a subset of M delta is, that will show that this union capital M, so this M delta is a subset of M. That's contradiction because of this. Okay, so this is the final contradiction, and this shows as the property uh, that every non-empty chain is contained in a maximal chain. Okay. This completes the proof of Sort's lemma. Let's go back up and see what was the contradiction. Okay. Okay. So the Sort's lemma is this is a partial loaded set such that every chain has a upper bound, and you want to show that this whole set has a maximal element. Okay, so okay, I think this is now. Let me write down the other one. Opposition. sounds lemma implies axiom of choice. So this one, we assume that sounds lemma is true, and we'll show that we'll prove axiom of choice. So the proof. So what you're going to do, what you're going to do, so to show axiom of choice, so let f from the set A to B here on function. Okay, so we need to show that there exists a function g from B to A such that you start with g and then you apply A. That's equal to this. So can complete the proof, and this is exercise 16. So what you want to do, you want to construct the this thing, but you look at you consider this L. This is F, sorry, call it H. The functions from B prime to A, where B prime is a subset of B. Okay, and note that so we can call these things like partial functions. Oh, wait. Let me write it properly. So you consider, so this these are functions h from B delta as B prime to A, such that B prime is a subset of B, and we have this condition F applied to H of B, H equals B for all B in B prime. Okay. Note that these things are so L is a subset of A cross B. I mean, I gave this thing as an exercise to verify that these are what I call partial functions, but these are partial functions that satisfies these extra conditions. Good. But the key idea is the partial functions are just subsets of the product set, and so and you can show that this is a partial order. Show that L under inclusion is a partial order. With the property every chain has an upper bound. Okay, upper bound comes easily by doing taking the union. Okay, and then by Son's lemma you get a function, and so exercise 16. So verify this one. Okay, so I call it exercise 16, and then exercise 17 show that if capital H in L is a maximum, is a maximal, is a then H is actually a function from B to A, and F goes to H equals identity of B. Okay. Good. Yeah, this is relatively easy to prove. Now, exercise 18. There are let me there are a lot of lot of like deeper questions that's happening. So we are kind of at we are dealing with the foundations, and actually we haven't reviewed the foundations. So the foundations are the axioms of set theory. Okay, so in these proofs, you're somehow allowed to use certain facts about set theory, and you're not allowed to use some other facts. So, and I will go into, I'll poke into those things when you write the solutions. Okay, so but let me do this. This is let a alpha uh, be a collection of non-empty subsets show that this product is actually non-empty. Okay, so this is again another you need Son's lemma for this thing. Exercise 19. Of course, the thing that I'm not telling you is what's the definition of the product for a general collection of sets. And so you look it up, and probably when you look it up, it will say that that by Sounds Lemma, this is not empty. So I mean, the real question is like, how do you talk about products of these sets? Okay. Now, what else? What else? What else? What else? I'll write down more problems. Uh, so basically, when you submit uh, solutions to these problems, and then I'll add follow-up questions, and that would lead you to uh, we need to do a review of the axioms of set theory. So we are following analysis 1 by Tao. Okay, so okay, so we'll do this thing later, not right now, but we'll do it inside Piazza. Okay, uh, later inside. And next thing, also I'm gonna skip this step 2. I have mentioned that in the syllabus that I will do transfinite induction. But I'll skip this thing for now. You can I mean, the point is like, I think if you're dealing with a practical problem, uh, you can, I mean, you have the tools for dealing with this. Okay, so we'll skip this thing for now, but I'll pick it up. I'll maybe put problems and in the homework that's kind of hint at these things. See, the whole one reason that I want to do this thing, which I'll do next time, I want to construct the I want to show you guys the construction of sigma algebras. Uh, Take like infinite unions, infinite intersection, like complements. You can do it like step by step, but you need more than countable. Uh, Not more than. You have to kind of do it like in countable many times, and then you have to kind of restart it. You have to go beyond. You cannot do it with induction, because induction goes all the way up to induction covers the integers, but then you have to do it one more time, and so that's a goal for me. So I'll pick it up and then I'll go through it. So there's a problem in probability theory book by Billingsley, and there's a couple of exercises in there that deals with this. We'll talk about sigma algebras I think next section or so. Okay, so I'm skipping the transfinite induction, and I'll put problems in the discussions that kind of digs into the axioms of set theory. And then the next thing is this one. logic and set theory. Again, this logic thing is a big deal for us. Okay, so but I want to see like I want to, let's say yeah, exercise. I mean, these things get like really interesting when you well, you have a existential crisis mathematically, meaning like this is like playing with that. Okay, so you'll have that in Piazza when you do homework problems and when I ask questions. Okay, so once you go there, you especially when you're playing in here with the axioms of set theory, you kind of get to like what are we allowed to assume and what are we not allowed to assume, and you kind of the definition is like always we kind of stay in a foundation. We don't question the foundation, but these type of things makes you question the foundation, and then the crisis is like when you don't know what the foundation is, like what things are solid and what things are not, and so on. So that yeah. Anyway, so here is something to think about. So we have this x and a, okay, and what about this thing? So this is a symbol in logic, right? So can we define? Can we do this thing? Can we do? So can we define this thing to be? It's a map between two. This is all the sets. So now we know the axioms of set theory. It's all the sets, and again, like yeah, we're trying to like let's say, I mean, we deal with sets that are of this format. Say A is a set, for example, A, B, and yeah, empty set. Okay, so uh, it is okay to consider the situations where this element that you're thinking, a set is an element in that. Okay, so let's have this and then have the set, let's say true or false. So can we do something like this? Right, so once you do a set theory, get a few or like what do we do with this symbol? How do you talk about this thing? Like when you want to talk about it, you want to kind of define in set theory, but can we do it? Okay. Uh, so I will leave it at this. Um, so this should get to the kind of the separation of logic and set theory. So like you ask the question like can this logic uh, stay independently of sets? Okay. like example. So you have seen things like this. For all x in R, there exists y in R such that okay, so the statement is not interesting. X plus y equals 1. Okay, or 0. Okay, and have seen things like this. And so you say this is the same statement as this for all x, for all y, x, uh, x in R and y in R. This thing implies x plus y equals 0. Right, you can try to show that these two things are the same thing, and we say that they're the same. Okay, but uh, but the point is this one we are very familiar, right? So when you do logic, we kind of throw in sets and these belong symbols. Okay, but this one looks like we have this x and y without restricting to a set. I mean, you have the this condition inside, right? So I want you to think about like yeah, think about this thing, like what's really happening. So is it the case that logic and these these symbolic manipulations, uh, uh, we have like a bunch of symbols and bunch of rules for manipulations. Uh, is it the case that you cannot like give a foundation to that in set theory? For example, when you have like groups, like when you work with groups, we have like all these uh, multiplication and the group operations and this and that, and you kind of bring in sets and we can define things and nicely, right? And but I'm asking, like, can set theory help logic to get rid of these like give meaning to these symbols for all there exist, or like belongs to symbol? Okay, so you'll carry out this thing too. And the thing is, unfortunately, given the von Neumann's second definition for mechanical system, so the logic is something that we cannot like skip. Okay, so it boils down to this. So what you're getting at, like the final thing. I mean, this is the most beautiful mathematical modeling thing. So you have a system like this, and uh, we have an observer, and he holds the stopwatch, whatever, right? Or like something. Okay, so he observes something, observe X, and he asks the questions like the X is like when you do experimental physics, you're measuring something. Okay, so we ask the questions with the, let's say, position. We have a ruler, let's say. is measuring whether the position of something is inside the set 1.1, 2.3, right? So no matter what, we have this type of statements, right? So these are like some propositions, and we want to assign the values to these things, whether they are true or false. And in quantum mechanics, you'll get maybe 75% of the time. So you assign a probability to each of the statements, but these statements would form a partial order in the sense that you will say this statement is bigger than this one, because whatever the value we assigned for this statement, let's say A and B, we have A is less than or equal to value of, let's say the you assign a true or false or probability, the that assignment has to satisfy this. It has to satisfy this ordering relation. Okay, so we have a partial order of statements like this, and as it turns out, that's and I hopefully I convince you that there is a partial ordering like this underlying, whatever the mechanical system you're trying to describe, like experimental one. I mean the physics that have to have it's built into the scientific method. Things that we're interested in are the ones that can be replicated and verified by different people, right? And so if you assume that setup, and this is the bare minimum. So all I'm saying, like the reason that we study partial orders and yeah, and these would have like additional properties and everything. So I'll go through those two. So all I'm saying that the logic part is kind of fundamental to this too, but the lattice part is too. And I think I'm at this point I'm done with the main tool in the world of partial orders. Okay, so let's go back up here. Yeah, so I did some things in here. Not all of it, but next I'll go through a whole bunch of different types of examples. Okay, and so far we have only partial loaded. We'll go through what a lattice is, Boolean algebra, logic, geometry, signal algebra. All that is kind of in the partial order world. I know that you have seen those in the space side, this side, but I'll get started here. Okay, and yeah, I'll put up. I'll hopefully I'll keep recording lectures and put in these things, and we'll try to have the regular lectures too. Okay, and yeah, I'll stop the lecture now.